How long will the locomotive run on battery power? Part 2. Part 1 is on my website. The address is in the description below. Unfortunately, only the user can determine the answer to that question. Almost every conversion to dead rail battery power is unique. There are several factors and variables that make a specific across-the-board answer extremely difficult. How to determine the answer to the question is presented here, as well as the results for two conversions that I did. To keep this information manageable, I am making statements with no explanation. To check my credibility and knowledge regarding this topic, I strongly urge the viewer to check out the website of my main hobby interest, radio control, electrically powered model airplanes, which is noted in the description below. Background information before starting the time voltage test procedure. 1. Lithium-ion based batteries are typically charged to 4.2 volts per cell when using an appropriate charger. Even right off the charger, a given cell will not read 4.2 volts. Within half an hour to an hour, the cell usually stabilizes to about 4.15-ish volts per cell. That's its resting, fully charged, stabilized voltage. The photo is of an IMR lithium-ion 10440 cell's measured voltage shortly after being charged. Number 2. After discharging, the cell's voltage starts rising and can take anywhere from half an hour to an hour to stabilize at a new resting voltage. Number 3, unlike a power supply, a cell's voltage is continually dropping through its entire use. It is not a constant voltage power supply. Number 4, lithium-ion batteries have a fully charged maximum voltage, as well as a don't go below this voltage or the cell will be ruined. Since the batteries used in both conversions illustrated here do not have low voltage protection circuits, the user has to determine when to stop using the battery. Number 5. Measured voltage values compared to some values on a capacity chart at various points during the discharge is not a very accurate way to assess the remaining usable capacity, runtime remaining, of a lithium-ion based cell. These types of charts can be easily found on the internet. However, measured voltage can be useful in determining how long a given pack should be run without dropping to a voltage level that would ruin the cell. This and the following graph shows somewhat typical discharge curves for lithium-ion based type batteries. I made the first one based on information from the previously shown chart by Mark Forsyth. The second one comes from Oscar Lang's website. I added a magenta colored line to both graphs. Please note the voltage at the position of the magenta line and its relationship to the discharge curve on each graph. Both graphs indicate that there is very little capacity, runtime in our case, left in the cell before it hits the knee and the voltage drops drastically. Therefore, 3.7 volts becomes a significant number. Determining safe battery runtime using a timed voltage test procedure. What the user needs: a converted and configured locomotive, a freshly charged battery pack, a timer, a device to read the voltage of a single cell, a loop of track to run the locomotive on, paper, and a writing utensil. The procedure. 1. Start the device that is to be used as a controller. 2. Plug the freshly charged battery into the configured locomotive and place it on the loop of test track. According to the LocoFi team, the decoder is pulling 0.05 amps on its own, just sitting there and on. Start up LocoFi. Run the locomotive at full speed with the light on for 10 minutes. 5. Stop the locomotive and immediately read the voltage of one cell. 6. Note the voltage on the paper. 7. If the voltage is significantly higher than 3.7 volts, Wait 10 minutes to allow the motor, decoder, and battery to cool down, and then repeat the running procedure for another 10 minutes. 8. Continue the steps of the full procedure until it becomes apparent that another 10-minute run will drop the voltage below 3.7 volts. The number of minutes derived from this test is not the runtime. The test results provide a base number from which to work. If the layout is fairly level and the string of cars behind the loco isn't too many, put 5 minutes less than the derived time on the timer and put the locomotive into normal service on the layout. If the layout has several or steep elevations and is pulling a lot of cars, it might be a good idea to reduce the derived time by 10 minutes. Once everything is ready to go on the layout, start the timer. Make some runs between points, do some switching, turn the sound and lights off if another loco is working. Do whatever is a normal working session for the layout. Stop working the layout when the timer goes off and immediately measure the voltage of a cell. That measured voltage can confirm whether the tested derived time is the real working time of the pack for this layout, too long, or whether there's enough capacity in the pack to have a longer runtime. Remember that the time for this test is the derived time reduced by 5 minutes or 10 minutes as previously described. If the cell's measured voltage indicates that a longer runtime might be possible, recharge the pack and increment the timer to what appears might be an appropriate time. Keep in mind that as cells age from usage, the cell's capacity decreases, which means that at some point, runtime will need to be reduced. My locomotives as examples: the Walthers GP15-1 CSX with a 3S 300 mAh LiPo installed in the locomotive. Runtime numbers for this locomotive were previously noted in the section titled Actual Battery Runtime on my HO webpage. They were noted as 10 minutes, 88% left in the pack, 20 minutes, 63% left in the pack, 30 minutes, 54% left in the pack, 40 minutes, 27% left in the pack. As noted now, the procedure has been changed to use voltage, not the percentage of usable capacity left in the pack. When this locomotive and battery combination was originally tested, only one speed step was used to configure it. The locomotive was reconfigured using 7 speed steps. The new configuration is shown. I changed the name to 12.0. It doesn't matter what you call it, as LocoFi has no way to verify the voltage. It's just a name I chose to represent a 3S lithium-ion battery pack. The step 7 speed is shown at 72 miles an hour, which is above the speed for the full-scale EMD GP15-1, which is 65 miles per hour. The max scale speed was set to 65 miles per hour. I did the time voltage test again on the CSX. The numbers are presented here with voltages, not percentages this time. 10 minutes, 4.044 volts, 20 minutes, 3.904 volts, 30 minutes, 3.821 volts, 40 minutes, 3.757 volts. A voltage check after the first 10 minutes of running using a LiPo voltage cell checker. The derived time remained the same at 40 minutes. Determining the usable runtime for the CSX LiPo combo. A timer was set at 35 minutes since the demo layout is flat and there is only a boxcar and caboose available to switch. The train was run in a prototypical manner, including picking up cars, running them point to point, dropping them off on sidings, etc. At the end of 35 minutes, a cell's voltage read 3.780 volts. That might be the runtime for this LiPo-Loco combination, or I might try to stretch it to 40 minutes next time. A photo of the demo layout. The Walthers GP15-1 Conrail with an IMR lithium-ion 4S 350 mAh pack installed in a gondola. The first time voltage test with the 4 IMR 10440 batteries. The voltages are when one cell was measured immediately after the run. 10 minutes, 3.883 volts, 20 minutes, 3.701 volts. I knew the CSX with its 3S 300 mAh LiPo had provided a significantly longer derived runtime, so I ran the test for the Conrail again. 10 minutes, 3.856 volts, 20 minutes, 3.667 volts. The derived time is then 20 minutes, but that is when I had an aha moment. The maximum speed for a full-scale EMD GP15-1 is 65 miles per hour. This locomotive was configured in the YouTube video, Making and Using a Portable Dead Rail Demonstration HL Layout Part 3. The screen capture is from the video. The last three configuration voltages produce miles per hour, well above what is required for prototypical operation for the locomotive. 72 miles per hour, 87 miles per hour, and 93 miles per hour. To reduce the amp draw and increase the runtime, the number of cells can be reduced. Yes, I noted reduced, to lower the applied voltage and thus drop the amp draw. Based on the new information from the CSX conversion, I changed the 4S IMR 10440 battery pack for the Conrail to a 3S configuration by clipping the red lead on the rear battery box that goes to the connector up front. The battery box red lead was soldered to the rear of the connector spring, and then the red wire run forward to the connector. The new red lead was positioned directly out to the side and then forward so that it could go to the connector and allow the battery being used only as weight to keep the gondola in the NMRA recommended weight range to still fit in the battery box. The battery in the battery box is not now part of the circuit. The Conrail was reconfigured in LocoFi for the use of a 3S IMR lithium-ion 350 mAh 10440 pack. Okay, this is the 7th step. I will let the train go around the track one time before I start the timer, and then we will see how to finish this up. Okay, next time around I'll start the timer. Start. Stop. That took 10 seconds. Ten seconds is entered. Backing out of it. Sets the speed at 65, which also happens to be the maximum speed that I looked up on the internet for this particular locomotive. I just have to get this set to 65, and now I do a save. And the last thing I want to do is I want to shut off the coast and the momentum for test purposes. I back out of here. And go ahead and exit. Oops, I can't exit from here. Go back to here. I can exit. Okay. I've turned the train back on. I'm going to start up the motor. Turn on the headlight. You have the horn of blast, ring the bell, and when the train starts to move, the speedometer will show the actual speed of the train. Which is running behind me right now. Take it all the way up to 65. And there it is at 65. And that's what 65 looks like on this little loop of track. And we bring it to a stop. Shut off the light. Whoops, I hit something else, I think. Don't know what's going on here, but we'll wait for it to happen. There we go. Manage. Shut off the light. Things can happen like that, especially when you're videoing. And shut off the engine sound. Two time voltage tests were completed using the newly configured 3S pack. During the battery test, this is what the train locomotive looks like. On the small loop of track, you can see the speedometer is at 65. It has been reconfigured to 12 volts. Two time voltage tests were completed using the newly configured 3S pack. Test 1, 10 minutes, 3.970 volts, 20 minutes, 3.834 volts, 30 minutes, 3.719 volts. Test 2, 10 minutes, 3.964 volts, 20 minutes, 3.831 volts, 30 minutes, 3.711 volts. Why is there such a time difference between the 3S LiPo pack and the 3S IMR 10440 pack runtimes? While the locomotives are the same type and from the same manufacturer, there is no way to really know if they are the same or not. The body shells were molded differently, so obviously they were from different runs. The gears could be tighter in one locomotive compared to the other. The 3S LiPo inside the body shell of the CSX only has short leads to the decoder in the CSX. The Conrail has long leads of tiny AWG wire from the gondola going into the decoder that is in the locomotive. The AAA battery boxes, which are not designed for this purpose, are less efficient than directly connecting cells together to make a battery. The good news is that by reducing the number of cells from 4 to 3 in the pack and the gondola attached to the Conrail was that there was a 50% increase in the time voltage derived runtime. A gain was expected, so it was worth the change, as the Conrail runs at a scale 65 miles per hour while drawing less amps for a longer time. The reason that the 4S 10440 pack was tried first was that it was simple to wire up the two AAA battery boxes, and the combined voltage of the 4 cells in series was within the LocoFi voltage specification. Modifying the boxes to provide 3 cells in series wasn't that much harder. The main problem was that I'd not remembered a very basic principle. If nothing changes in what is causing the load and more voltage is applied, the amps jump way up. I should have realized that a 3S pack would have sufficed based on the first conversion of the CSX to a 3-cell LiPo. Determining the usable runtime. A timer was set at 25 minutes since the demo layout is flat and there is only a boxcar and caboose available to switch. The train was run in a prototypical manner with picking up cars, running them point to point, dropping them off on sidings, etc. At the end of 25 minutes, a cell's voltage read 3.780 volts. Pure serendipity. That might be the runtime for this IMR 10440 lithium-ion battery local combination, but a second run was made in a prototypical manner. The timer was set for 30 minutes for this time test. That was a 5-minute increase of time over the first run. After the 30-minute prototypical run, a single battery voltage read 3.684 volts when immediately pulled from the gondola. 1/2 hour later, the cell read 3.711 volts. This clearly demonstrates the voltage bounce back after the load is removed. Obviously, having more sets of multiples of 3 of the IMR 10440 lithium-ion batteries charged can extend the runtime, and with this setup, they are easily and quickly swapped, even with a dummy removable load covering them. What did these two runs of the 3S 10440 pack prove? For my flat layout and a couple of cars that had been set to the NMRA recommended weight, I feel that I can safely run this unit for half an hour, but that is just for this particular unit with my cars on my layout. With 6 of these lithium-ion IMR 350 mAh 10440 cells charged and ready to go, the runtime doubles with a simple replacement of the used cells with a fresh set. At this time, I believe that the dead rail conversion using LocoFi and the 3S IMR lithium-ion 350 mAh 10440 pack has proven quite feasible, relatively easy, and relatively safe to do.